Hey, this is LiveOverflow. This is another video write-up of another challenge of the 32C3CTF, and it will be the pwnable teufel challenge. Like the README challenge, I didn't solve it during the CTF, but I used the write-ups to work through the solutions, and now I understand it completely, and now I want to share the knowledge that I gained with everybody else. So I will now show you a recording of me creating the exploit step by step, and I will explain certain things along the way and basically comment on it. So first thing I do is I just connect with Netcat to the service and get a view on it. So it looks like you type something in and it responds the same thing back again. So it's not very fancy. Like in the previous video, I explained I use Vagrant as a virtual machine wrapper to quickly set up machines to work with. In this case, it's a Ubuntu machine, and yeah, I just like set up my environment here, and I create a symlink from the Vagrant share folder, which is shared between the VM and my system, inside of my CTF script folder. So just to it's just easy setup for my editor to create scripts and stuff. So now I copy the link, and I'm now on the Ubuntu VM there on the right, and I download the file and I extract it. And obviously one of the first things I always do is I check the file type of it, and indeed it's a 64-bit Linux executable, but we also get a libc file with it, which is an indication that it's probably ROP, return-oriented programming, or return-to-libc kind of challenge. Why they usually provide you the libc binary, because you often have to find the gadgets in there. Okay, so I have it now up in my VM, the teufel, and it also runs on my machine, so that's great. And yeah, now I can open it in Hopper and we can start having a look at the assembler code. The first thing I notice is that there's the entry point, the entry procedure function, and below it is another function, and then there's nothing. That's literally the whole code segment. You only have the entry function and the function below, and then directly afterwards there starts another section. So it's super tiny binary, probably handcrafted. So what we see is this entry point calls mmap and then mprotect. So if we look here at the decompilation, we see that it calls mmap with 0 as the first parameter, means that the kernel will decide on an address that it will give to us, and it will be 3000 hex big. And one of the other 0 parameters there means that it will have 0 protection, nothing set. You will see later in the S-trace what those protections exactly mean. And then we have an mprotect, which changes the protection flags on a certain memory area. And if you look here at the output, you see that there's a loop, and I will always around this one function, so I call this endless loop. And this endless loop has two reads and a puts call. So it basically just reads something and then puts out a value. Now we can have a look at it with S-trace, because it will show us the mmap call. So we can see here that we request a new virtual address space, and we get this address which starts at 000. And then afterwards we call mprotect with D000, so it's 1000 hex further. That was the plus 1000 in the decompiled code, and it sets those as read and writable. And if you now look at the program memory map output, you see here starts the address, and then there come two more entries afterwards. So basically you have a read writable area in the middle, and you have two guard pages with no protection around it, and that will become important in a second. And you can also see that when you input something, it will always read 2 times and then write something. Yeah, so you can here see the calls again. You got 2 reads and a write. So now let's throw this in GDB again and set a breakpoint at the entry point, and then we can step slowly forward to the mmap call, and we can see here again nicely the parameters that it gets called with. So it will allocate 3 hex 3000 range of memory. Now we will set a breakpoint after the mprotect. So now it will have created this middle page surrounded by those middle page with read and writable access. And you will also notice it moved the address that was just set with mprotect into the stack pointer. And maybe you can like set back a couple of seconds and look at the stack output here at the bottom left, that the stack is now pointing to a different address. And this is pointing at our memory mapped area that is read and writable. So we move the stack somewhere else now. And then we will call now the endless loop, and it will use this new stack. So we'll place now a couple of important breakpoints, basically before every read, and then also before we return. This allows us to always inspect the stack at certain different stages, so we can see what happens. So let's move to the first read. It reads 8 bytes into an address that is on the stack at FE8. And you see only here, like on the bottom left on the stack output, that it like literally has only 3 values on the stack, and the other one are white. Those are different. Okay, so we insert an A, and then it did a second read with the size that we actually entered with the first read. So you can see here I entered multiple A's, and now you can see that the second read will read like 414141 bytes, tries to read. So that means that with the first read we specify how many bytes we wanna read into, and with the second read we actually read those bytes in. And then obviously we can say we wanna read 200 bytes. Or when we type an A, we basically say we want 41 bytes to read 41 bytes, and then we can enter 41 bytes and basically overwrite the whole stack. If you look now what I'm doing here, I'm just basically playing around with different values, because depending on what you enter with the first read, the program will actually exit. And I haven't investigated this properly, but as far as I know, the read will check if it makes a sanity check if it can even has that much space to read into and stuff. And because the memory region afterwards has no protection at all, the read will probably just exit, because it will not be able to read there. And in this example, I filled the buffer perfectly with the new line at the end, but the string ends with a 0 byte. So it tried to put the 0 byte in this memory region at 7000, which is not writable, so it will cause a seg fault. So if I'm more careful and put a little bit less C, we can see now that we didn't completely fill the stack, but we did overwrite the return pointer. And now we also have currently a break pointer at the red. And if we now step one further, we will obviously return into the C's that we have written on the stack. So this means we can fully control the instruction pointer. Then what I'm doing now is I'm basically showing off ASLR. If you check the libraries that are linked to this binary, you see that with every time we execute it and check the address it gets mapped to, they are different. So it means that the libc binary will be always at different regions. And if we look here on the stack, we also notice that there is a value on the stack which is the stack address. And what we can do here, we can leak this by, because it will print the string that is on the stack. And if we fill the first 8 bytes with A's, and then the last null byte of it with another value, we will force puts to also print the address that is on the stack. And I'm demoing it here on the right on the shell with the simple echo. We read the first 8 bytes, which is the A, and then we read 8 A's and a B, which will then force the puts to also print the address that is stored on a stack. So basically this allows us to leak the stack address. So now I'm starting to write a script here, because it clearly will be more interactive, because we have to leak the stack address and do calculations on those addresses, and because of ASLR it will always be different. So we cannot do a simple static program, we have to do it with more interaction. So what I'm doing here is I create a little wrapper function X that basically just calls struct pack to build those nice addresses. And basically I'm just rebuilding what we just did by hand. We write for 1 and the new line, the A for 1, and then we write 8 A's and a B, which will cause the stack address on the stack to leak. So I have to save it in the correct place. Okay, so yeah, that looks fine. Now let's even throw it at the target and see if that actually works too, if we can leak the address. And with text, maybe looks more. You can see it more. You can see it better. That indeed it looks like that we can actually leak the stack address from the target. As I said, we need a little bit more interaction, so we actually have to like do some socket work and do the connections with Python. So what I'm doing here, I create a socket and I define the server address up there. And we will call this connect server, and it will return the socket that we created for us. So we can just connect the socket and use the socket to send the buffer that we just created. And with receive, we can print whatever we received. So when we now call Python teufel, it will actually create a socket to the server, and yeah, seems to work. So what we now want to do is I create a function that will read all the bytes that are available. I call it receive all. And what it does is just basically looping around receive and read and append the bytes to B, and in the end return B. So this will read all the available bytes that we have. So if I execute this, receive all, you will notice I get a timeout. That's because I set a timeout in the setup of the socket, and obviously I have to catch this in case it happens. And that's fine. That will happen basically all the time. If that happens, we finished reading, and we can now return the whatever we have read. So this is just it seems to work okay, because if you read too fast, you sometimes read garbage values, I have noticed. So that's just something that seems to work better. Okay, and then I just add some nice output that it becomes clearer what's happening. Okay, looks cool. So now we want to convert this to a proper address, to basically a number, so that we can calculate with this. So I could, be intelligent and do this like first try and realize how to convert this, but it's more try and error for me. I define another wrapper function with unpack, so I can unpack this binary string into a number. But obviously it's not 8 byte long, and I have to add some 0 bytes. But because I'm a noob, I cannot calculate this. I have to do trial and error to figure out where I have to append the padding, the 0 byte padding. Oh, failing here at standard Python, but in the end it seems to work, just that it doesn't look so correct with the zeros at the end. I think the zeros don't really belong there. I also decrease the timeout because it always takes so long to wait. So now I want to test it locally. So I use socket again to basically act like the server maybe would do. So I can execute this, and now I can connect to like localhost, and it's now I can easily debug it. So now I want to print the memory map of the teufel process that I call, but because the script finishes, the teufel binary will also quit. So before I close the socket, I will add a wait with raw input, which allows me to check the memory map. And then I notice that the stack address is not completely correct because the 0 bytes were not correct. But yeah, now that looks actually pretty good. If we check here, the stack will have the correct value, and we successfully leaked the stack address. Now we can start to find the gadgets, because we can leak the stack address and we can control the instruction pointer. So now we have to basically increase the space on the stack to do more complex stuff, because we only have one address we can use. So we are looking for a gadget that will somehow modify the stack pointer, and the basic idea that I have is moving the stack pointer further down so that we get more and more space. But not too far down, because then we don't control the values on the stack anymore and we don't know where to return into. So we basically just reduce the stack a little bit, and we still have some values on the stack that we control, and then we return into the endless loop. And yeah, this gadget here does moves the base pointer into the stack pointer, and when you can see that before this function returns, it pops the base pointer. So we fully control the value of the base pointer. In this case, it's b. And now I just emulate the overflow, and indeed we control the base pointer, and thus with this gadget we control the stack pointer. So now we can set the stack pointer to any value we want. And what we want to do now with it, we want to move the stack a little bit higher than it currently is. And then we call the endless loop again, and then basically everything is one address higher on the stack. And we can again read new values, do the overflow, and then basically do the exact same thing repeatedly and slowly move the stack upwards. So I know it's a little bit complex. I mean, this, especially if you have not much experience with return-oriented programming, and I'm sorry if that's rambling, it's just confusing, but if you would do it yourself by hand, then it would be clear. So yeah, our design would be that we use a gadget to move the stack a little bit higher, and the new stack address value will be basically the b's, which yeah, will be now our new stack pointer. So again, we write 3 addresses. The first one will actually be now, instead of the a's, that was previously the a's, will now be the address that we want to return to. And the next value will be the new stack address, so we will move the stack a little bit higher than it used to be, and obviously the actual overflow down there, the from our gadget. So I hope it becomes clearer when we now debug this a little bit. Yeah, I try to now calculate the exact address I want to set the stack pointer to move it a little bit higher. And you know, I try to be intelligent and calculate it, but somehow I screw this up and I cannot figure it out. So basically it's a trial and error again to get the value right I want to set the stack to, that it works what I want to do. Okay, so I think, yeah, now I calculated and now I get the correct address. So now pay attention. So we will break at the return. We will have the new stack address in RBP, and so we will return to our gadget. We will move RBP into the stack pointer. Pay attention, we will update it now. Now the stack pointer points to a new address. And if you look closely now we see we moved the stack up. Like before there were no yellow values on the stack, now there are multiples. And if we step further into the next gadget, yeah, we pop the RBP again, and now we will return to the next address on the stack, which is now the endless loop function again. So now we basically moved the stack one address up, and we are at start again. And we can now repeat this in a loop to move the stack further up and up and up. So let's create a loop around this. Okay, so in step of 8, and we will constantly want to change the stack address. Do some changes here. Again, for now we test this, and when we now continue, you see how slowly the stack grows bigger and bigger and bigger. And now we have enough space on the stack to actually put like multiple gadgets or whatever we want to do with it. So basically now we have all the possibilities of ROP. I mean, the ROP exploit that we will use is not that complex. We don't need that much space, but you know, it's actually cool to see this loop happening and making more and more space on the stack. And I will wrap this again in a function called build stack. It will take the socket, and so every time when we call this function, it will leak the current stack value, and then with this value, we slowly will build the stack. Cool. So now we have a setup that leaks the stack and creates space on the stack. We can check the memory map again if the memory we leak is correct. And yeah, looks all fine. So now we have to figure out where libc is loaded. To do this, I've now read the memory map a couple of times, and now I take notes of where the libc address is and where the stack address is. And then we will have a look at this with the calculator and calculate the offsets between those things. So if we calculate how far away the stack is from libc, we notice that it's both time the same. And notice, like when I say stack, it's not the usual stack. This was a memory mapped area that we created. So, and this attack or this issue is called offset to libc or to any other library or whatever. So there's always this constant offset happening from an area, from a virtual address space that we map. And that is fixed for like this particular, I guess it's dependent on the libc. So it's for my local libc, it's this offset. But now we have a problem. We have to figure out the offset of the target system, because this will likely be a different offset value. So how we can do this is we try to leak an address that is from libc. And we can do this because the teufel binary uses the exit function, which is from libc. And I also now copy my local libc to a file so I can load it in Hopper and find the exit symbol in there. So I want to know the address of exit, which is used by the teufel binary. So I can go into the global offset table from teufel and get the address of exit. So here in GDB we can read this address, which ends at 2D0, and we can compare this to the exit symbol from the libc, which also ends at 2D0. So they are at the same offset, and we can write this address down because this is the offset from the start of libc where the exit function is. And what we can do now is we can reuse a little bit of code that is already in the binary, and that is the puts call. Basically, we want to leak the address from the global offset table of exit, and we can use the puts call for that. To do this, we can just jump here right before the puts call, because we have to set the RDI register with the address of the string that we will print. In our case, the address will be the global offset table entry for exit, so that it prints the access address. We have to set it up in a way that the third value will overwrite the instruction pointer. This will be where we want to jump to right before the puts. The value before will be the value that will be loaded from the string that we want to print, which is the address of the global offset table of exit. And then we just have some A's that we don't care about. So if we test this now, it doesn't work. Like the value we get is just wrong. And that's because I first of all made a mistake, and I again didn't send it, but the values are not correct. So I open it in GDB, I attach to the GDB process again and check it out. And now we are right at the puts, and you can see that it subtracts 8 from the base pointer. So now the base pointer is currently pointing exactly at the exit value from the global offset table, but it subtracts 8 from it, and that will be loaded in RDI. When we step one further, we will see that now RDI has the wrong value. So it will have the wrong value. So we'll have to add 8 to it, that after the subtraction it will be the correct address. So you can try this. And yes, now this value looks much better. You get the 7F there, which pretty much looks correct to a libc address. Now we have to do the same thing again like before with where we leaked the stack address, fiddling around with converting it to a proper address. This is so ugly. I am very sorry for this terrible code, and with some trial and error, like it's the worst. I'm sorry. But at some point it almost works, except that I accidentally stripped away the last 2 bytes, the D0 in this case, which is now missing, and I realized that, I guess, soon. Still not correct, but almost correct. Yeah, now it looks good. Okay, so now we can calculate the offset to libc by basically subtracting the stack with the offset with the leaked exit address, And then from there we subtract the offset inside the libc binary to the exit function. And you can see here when we print this value, it's what we have calculated before. So now we have a way to leak the offset to libc. And we prepare now the important offsets for the target binary, which we can already do here. And then we can also try it with the target and see if we can, if that works. But again, I have some coding error here, accidentally print offset to libc before it was defined. So I move that to the correct location, try it again. And yes, it says here that libc is added in that place, and it also calculated an exit offset, which is actually different from our local system. So cool. That is the offset to libc on the target system. Okay, now we want to prepare our ROP or our return to libc exploit. First of all, we have to find the string bin_sh, because basically we want to call system bin_sh. So and we can actually find this in libc. And then also we need the address of system. And we can also already get those values for our target system as well and get all the offsets ready. You see also they are a little bit similar, but still different, you know. That's why it's important that the challenge gave us their libc, because the addresses just are not the same on different systems. Okay, so now with the first stage of the exploit, we found out the offset to libc. Now we make a second stage where we use this offset to actually do the ROP exploit. But first we have to figure out how to call system. So I do this little C program and look at the disassembly, which tells us that we have to load the string that we want to execute with system into EDI, and then we call system. So we have to find a ROP gadget that will pop a value in RDI and then return, so we can return to system. Again, I use ROP gadget for it, and this time on the libc. And we are only looking for pop red because I'm looking for a pop RDI red gadget, and I saved it in a file. And I do the same with the target libc. And this takes a while, so we start to prepare the exploit in the meantime. So basically, again, we want the same thing, but we don't care about these values. And the first gadget we will return to will be pop RDI red. The value that we will pop will be the offset of, will be the address of bin_sh string. And then we will, after that, return to system. So now we have to just wait for the address of pop RDI. And I also change some, prepare the code for the actual exploit. Okay, fixing some small things. And it looks like the ROP gadget program was ready. So let's find a pop RDI red gadget. So there we have it. So let's define it for my local system. And now let's also get it from the for the target. Cool. So now we can place the pop RDI gadget address there, and we can try it on my local system if it works. No, didn't work because I'm a bad programmer. What did I forget? Also, here's a cool trick that I learned from GeoHot's CTF streams. You can use telnet-lib and assign it the socket that we created, and then you can use telnet interact to have an interactive shell with the bin_sh would work, which is still not working. And it takes me a second to realize my mistake, because if you look here, which libc address I used to calculate the addresses are from the previous stage. I'm debugging it now, and I'm looking at the GDB and realize that the values are incorrect. Here I'm breaking here at the return, and when I look at the address that we were returned to, they are completely gibberish. They are not where libc actually is. And then it clicked, and then I realized I calculated the libc address based on the first stage, but obviously we close the socket again and open it up, so it's different. And now it's magically working. We throw it against the server, but it doesn't work. What the fuck is my mistake? Now, do it again, and then I realized it works. The issue before was that it read some garbage addresses, which you can see there at the stack and libc output address. They are incorrect. But yeah, now it works. The flag is move pop red. Repeat, that's exactly what we did to move up the stack. And there's our flag. Awesome, we got the flag. I'm very happy. I learned a lot, and I hope I was able to share some of it with you, even though that this teufel challenge was not so easy to understand like the readme challenge before, because this included so many more steps and ROP exploit, which is kind of ugly to explain, but I hope that you learned something nonetheless. Please check out the Reddit threads from about my videos. You can comment there, and I'm very, very interested in little tricks, techniques, and scripts and stuff that you are using to solve challenges like that. If you have just like little tricks that you could use in GDB or in Python or whatever to just speed up things or get things more reliable, or how you do those address calculations where I kind of did trial and error stuff, I'm always looking for tips to improve myself. So that would be pretty cool if you would share that in the Reddit threads of the particular videos. Thank you very much, and hopefully see you soon.